The addition rules for probability. First addition rule. A utility company owns 420 vehicles. There are 120 cars and 300 trucks. The intended use of the vehicle determines its color. The breakdown is shown in the table below. Let's find the probability that a randomly selected vehicle owned by this company is a blue car or a white truck. No vehicle in this fleet can be classified both as a car and a truck. Therefore, the two events, a car is selected or a truck is selected, are mutually exclusive. The addition rule for mutually exclusive events is the probability that event A or event B would occur is equal to the probability that event A would occur plus the probability that event B would occur. So in probability notation, we would express this as the probability that a blue car or a white car would be selected, since these events are mutually exclusive, would be equal to the probability that a blue car will be selected plus the probability that a white truck would be selected. There are 40 blue cars out of 420 total vehicles, and there are 100 white trucks out of 420 total vehicles. The probability then would be equal to 140 out of 420, which would reduce to 1/3. Second addition rule. The table shows the gross for movies of 2016 that received a rating of PG-13 or R. If a movie from this group is selected at random, what is the probability that it is rated PG-13 or grossed at least $100 million? We can express this in probability notation as the probability that a randomly selected movie is rated PG-13 or grossed at least $100 million. Since these two events can occur simultaneously, they are not mutually exclusive. The addition rule for events that are not mutually exclusive is given as the probability that events A or B would occur is equal to the probability that event A would occur plus the probability that event B would occur minus the probability that both events A and B would occur. So the probability that a randomly selected movie would be rated PG-13 or grossed at least $100 million would be equal to the probability that a randomly selected movie is rated PG-13 plus the probability that it grossed at least $100 million minus the probability that it was rated PG-13 and grossed at least $100 million. There were 138 out of 360 that were rated PG-13. There were 19 out of 360 that grossed at least $100 million. And there were 15 out of 360 that were both rated PG-13 and grossed at least $100 million. So this probability would be 142 out of 360, which will reduce to 71 out of 180. Let's go ahead and follow along with your notes. Mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. That is, events that have no outcomes in common. These are also known as disjoint events. Events that can occur at the same time are not mutually exclusive. Example: are the events mutually exclusive? Determine if the events are mutually exclusive and which events are not. Rolling 2 dice. If we let event A be a roll that has a sum of 7 and event B being rolling doubles, well then these are going to be mutually exclusive events. Because clearly, if you roll doubles, like a 3 then a 3, those add up to be 6. Or a 5 and a 5, that adds up to be 10. Anytime you roll a double, you get an even number, which clearly would not be a sum of 7. Therefore, these two events could never occur at the same time. Therefore, mutually exclusive. Select a registered voter. Let's say we were to choose a voter at random from a group of individuals. Event A is that the voter is registered as independent. Event B is that the voter is registered as Republican. Well, since you cannot be an independent and a Republican at the same time, then also these events are mutually exclusive. Once again, meaning events A and B cannot occur at the same time. How about drawing one card from a standard deck of playing cards? Event A is selecting a face card. Event B is selecting a heart. Well, as many may know, selecting a face card could mean that you selected a face card that was also a heart. For example, the Jack of Hearts, or the Queen of Hearts, or finally the King of Hearts. Since it is possible to be both a face card and a heart card, these events are not mutually exclusive. When you have two events, A and B, that are mutually exclusive, the probability that either A or B will occur is as follows. You simply add the probability of A to the probability of B. This is the first addition rule. Note here in the diagram that there is nothing in common between A and B. They are disjoint events. There is no overlap. At a convention, there are 7 mathematics instructors, 5 computer science instructors, 3 statistics instructors, and 4 science instructors. None of the instructors teach in more than one discipline. If an instructor is selected, find the probability of selecting a science instructor or a statistics instructor. Now, once again, it says that none of the teachers instruct in more than one discipline. That means there is no overlap. For example, a computer science instructor at this particular convention does not teach mathematics, or vice versa. Let's go ahead and note there are 19 instructors present. Event A is being a science instructor. Event B is being a statistics instructor. And since this is the case, and also since a science instructor does not teach statistics and vice versa according to the problem listed above, so being that these events are mutually exclusive, the probability that you are selecting A science instructor is 4 out of 19. Added to the probability that you select a statistics instructor, which is 3 out of 19, gives us 7 out of 19, or 0.3684. Second addition rule. This rule is when events are not necessarily mutually exclusive. When two events, A and B, are not mutually exclusive, the probability that A or B will occur is as follows. Notice here that it has the same language on the left-hand side as the previous addition rule. However, because the events are not mutually exclusive, it has a slight difference to it. It starts off exactly the same, the probability of A plus the probability of B, but then it subtracts the probability that both A and B occur at the same time. What this does for us, it subtracts away any sort of overlap or overcounting. Note here that this rule can be still used when events are mutually exclusive, as long as you recognize that the probability of event A and event B occurring at the same time equals 0, because they cannot occur at the same time. So really, the second addition rule can be used in both instances, where the events are not necessarily mutually exclusive or even mutually exclusive. When two events can happen at the same time, the probability that both A and B occur is included in both the probability of A and the probability of B. So by not subtracting this fact means you are going to overcount that probability. When events are not mutually exclusive, you'll notice here there is some overlap, and you don't want to double count. That is why you subtract the probability that they both occur at the same time. Example. Suppose there is a study involving 300 patients. Of the 100 alcoholic patients, 87 had elevated cholesterol levels. Of the 200 non-alcoholic patients, 43 had elevated cholesterol levels. The results are summarized in the table below. Let's go ahead and find the following probabilities. Let's find the probability that we have an alcoholic with elevated cholesterol. This will equal to the number of patients who are alcoholic and have elevated cholesterol at the same time, divided by the total number of patients surveyed. Well, as we can see in the table, this will be 87 patients out of the 300, or 0.2900. Let's find the probability that they are non-alcoholic. Well, that would be simply the number of non-alcoholics divided by the total patients surveyed. So in this case, 200 out of 300, or 2/3. Now here is where I introduce the word or. So we must actually note, are these events mutually exclusive or are they not mutually exclusive? Well, these events are not mutually exclusive. And the reason why they are not mutually exclusive, because according to the table, you can have a patient that is alcoholic and has elevated cholesterol. For clarity, here's the table. Here, we're looking for the probability that a patient is alcoholic or with elevated cholesterol. The patients that are alcoholic are represented in this row here, and the patients with elevated cholesterol are represented in this column here. Now, there are students who may think that the only number that matters in this particular case is the 87. since that's where they intersect. But that's not what the question's asking in this case. Remember, this is asking for the probability that the patient is either alcoholic or with elevated cholesterol. So as I solve this problem, please notice which numbers I use, and perhaps even more importantly, which numbers I do not use to solve this problem. I'll go ahead and highlight the numbers I refer to, including the 300 here. Again, please pay close attention to which numbers are used and which numbers are not used. So because these events are not mutually exclusive, we need to calculate the probability that the patient is alcoholic plus the probability that the patient has elevated cholesterol, but then we also must subtract the probability that they both occur at the same time, because once again, we do not want to overcount. Once again, let's go ahead and calculate the number of alcoholics divided by total patients surveyed, plus the number with elevated cholesterol divided by total patients surveyed, and then subtract the number who are alcoholic and have elevated cholesterol divided by total patients surveyed. 100 over 300 plus 130 over 300 minus 87 over 300 according to the table gives us 0.4767. Once again, here I use the word or. What's the probability that the patient is not with an elevated cholesterol or is an alcoholic? And once again, these events are not mutually exclusive. According to the table, you could select a patient that does not have elevated cholesterol but is also an alcoholic. For clarity, here's the table. Here, we're looking for the probability that the patient is not with elevated cholesterol, which would be this column, or the patient is an alcoholic, which would be this row. Now, some students would think that 13 is the only number that we need to consider, but 13 represents the number of patients who are both alcoholic but also do not have elevated cholesterol. That's not what the question's asking. The question is asking us to find the probability that the patient is not with elevated cholesterol or is alcoholic. There's a potential to double count here. So we must use the second addition rule to fix this. So be sure to take note of these other numbers that are in these rows and columns as I solve this problem. Also, please take note that some of these numbers will be used and some of these numbers highlighted will not be used. So once again, we calculate the probability that the patient does not have elevated cholesterol, add it to the probability the patient is alcoholic, and subtract the probability that the patient does not have elevated cholesterol and is an alcoholic at the same time. This gives us, of course, 0.8567. The probability that a customer selects a pizza with mushrooms or pepperoni is 0.55. Note the word or. And the probability that the customer selects only mushrooms is 0.32. If the probability that he or she selects only pepperoni is 0.17, find the probability of the customer selecting both items. Now this is a unique example. Here they are asking us to solve for the probability that both mushroom and pepperoni occur. Note that in the example above, they tell us that the probability that the customer chooses mushroom or pepperoni is 0.55, and that the probability that the customer chooses just mushroom is 0.32, and also the probability that the customer chooses just pepperoni is 0.17. Now, since there are customers who definitely put both mushroom and pepperoni on their pizza, these once again are not mutually exclusive. So to solve for this particular example, we go ahead and remind ourselves of the second addition rule, which I may say once again, you can actually use for either mutually exclusive events or non-mutually exclusive events. This rule works for both situations. So once again, since we are given most of the information here, let's replace what we know and solve for what we don't know. So quite simply, solving for the probability that they choose mushroom and pepperoni gives us 0.06.